You throw away a pressure vessel every day. It holds roughly 6 atmospheres behind a wall thinner than a sheet of paper, and it almost never fails. This is the rarest drawing in the catalog, the one that didn't break. First, the record, and for once, it is short. No lives lost, no injuries, nothing to mourn. We begin here, quietly, the way every drawing in this catalog begins, with what it cost. And this one cost almost nothing to keep you safe. Now the design, working. Look at the numbers. A wall about 1/10 of a millimeter thick, internal pressure near 90 pounds per square inch at the limit, and a mass today of just 13 grams. It should not be possible. It is routine. It is one seamless piece. A flat disc, punched out, drawn into a cup, then driven through tighter and tighter rings that iron the wall thin and stretch it tall. No side seam, no welded line down the body to fail. Start to finish, about 1/7 of a second. If you like things explained instead of sensationalized, subscribe. A new drawing is filed every week. Most of them broke. This one is here to show you what it looks like when nothing does. Here is the trick the whole thing turns on. You would think the pressure inside is the enemy of that paper-thin wall. It is the opposite. The pressure pushes the wall outward and holds it in tension, and thin metal in tension is strong, like a chain pulled taut. Engineers have a name for this, a pressure-stabilized structure. The same idea once held up rockets, thin tanks that would crumple empty but stood rigid the moment you pressurized them. Your soda can is built on the same logic as a launch vehicle. Now turn it over. A flat bottom would bulge under pressure and pop out, so the bottom is drawn into a dome, curved inward, a tiny pressure vessel of its own, like the base of a champagne bottle. The curve spreads the load, so a thin floor can hold a lot. At the top, the most expensive part, the lid, is made smaller. The body is necked in over about 11 gentle steps to a narrower rim, saving metal on every can ever made. Then a double seam folds lid and body together, airtight, no welding. There is exactly one place the can is meant to give way, and only when you ask. A scored line, deliberately thinned, anchored by a rivet pressed from the lid's own metal. The tab is a lever. It vents the pressure first, then folds the panel in. A controlled weakness by design. So how do you actually break it? You take away the very thing that made it strong. Open it. Empty it. A full sealed can will support well over 100 pounds straight down its length. You can stand on one. The same can, empty, folds under a fingertip. Here is the failure line, the one this drawing ever earns. With the pressure gone, the column strength goes with it. A small push and the empty wall buckles and folds. The strength was never in the metal. It was in the pressure. The other ways out are just as honest. Overheat it or freeze it, and the dome can pop convex, overpressure beyond what the curve was tuned for. Drop it, then open it, and the gas escapes in a rush. Every failure here asks you to first undo the design. And here is the quiet triumph. In the 1960s, this can weighed about 85 grams. Today, 13, roughly 1/6 of the metal, holding the same pressure. No disaster forced it. An industry simply removed material year after year and never let it fail. Failure mode, none, by design. The only way to file this one was to take the pressure out. Nothing breaks without a reason. Now you know why this one doesn't. Drawing filed.